All right. Hey, well, I'll get us started. I'll repeat what I said last time, and I think you know this, but we are trying to go kind of quickly here, punch out a whole chapter a day, and that's more than we normally do, and not only this semester, but normally in other semesters. We do about a chapter a week. But for this first unit, as I commented here, it's trying to get these mechanical waves. If there's any material we can push fast or not quite get to, this is a good category for that. So that's why I set it up this way. It's kind of too bad it's at the beginning, but that's, like I said, kind of the best way here. So as I was skimming through the notes this morning and kind of looking at this, I got feeling that we're probably in pretty good condition, that we can get all this done today. The biggest question will be then, will there be any additional time to do example calculations? That's kind of what I'm hoping that there might be. So let me jump right into sound waves here. This is that next chapter, and I commented that we did chapter 16 on Tuesday, and we'll do 17 today, and then we'll do 18 on Tuesday. And so quick 3 chapters there. Some of you have been asking about the homework, and I would say, look, if you need the weekend to get it done, fine. I completely understand that. And so some of you had finished 16 thinking it was due today or rushing, and others of you emailed me, and I'm just going to say, look, if you got it done, you're probably much better off and in a better situation, because now we're going to go into 17. But if you're not done with 16 or didn't even think about doing it or having the time to get it done, completely understand, and especially if you wanted Dawn to help you on Friday, that's fine. The only, like I said, word of caution is you're kind of working on 2 chapters this week here, and so try to get 16 and 17 done by next Tuesday. Definitely 16, but if 17 needs to linger a little bit, so be it. And then next Thursday, we're going to get started into 19. That will get us started. Now, that won't be on the test. That will shift gears. We'll go into thermodynamics at that point. And then we will slow down our pace a little bit. Then we will do 1 chapter a week. Yeah, and then so we have the Thursday for 19 test, and then 19 again. And so that we'll be done with 19 at the end of that first week after the half test. And maybe even a little bit further, because the easiest chapter of the next unit is 19. And so if there's anything we can get accomplished a little early in 19, that would be beneficial for the next chapters, because we don't want to rush those. Those are demanding chapters. All right, well, as I pointed out here, we are going to deal with sound waves today. And sound waves is a natural extension of the last chapter we did, where we worked with waves in general. And now let's apply all that wonderful stuff that we learned on Tuesday to a specific case, which are sound waves. And then later on we'll do light waves, and later on we'll do material waves after that. But if I put here, what are sound waves? How do you answer that? And this is the mental picture I want you to have. If you can keep this mental picture in your mind, together with the general properties of waves that we've been doing for the last chapter, I think everything else will kind of fall in place. So you might have noticed that I brought out this wave machine. Actually, it's backwards. Not that it matters too much, but we put these fancy orange stickers on there. And so if you can see these orange stickers, they are supposed to represent an air molecule. And so if I took an air molecule and touched it and pushed it over, what would it do? It would move over and collide with the second, right? First one would stop, second one would move. Then the second one would move over and hit the third. Second one would stop, third one would move. So forth and so on all the way down. And so eventually this molecule would move. And so here I have transported energy from point A to point B without the material moving from point A to point B. And hence it is a wave. And this kind of motion is our sound wave. And so that's the answer to our question. And although we can't see these molecules or these atoms moving, the answer I like to give for what are sound waves is say it is simply oscillating atoms. Atoms moving back and forth. And so one atom, then hits another atom, then hits another atom, then hits another atom. And this can continue on. And does it necessarily have to be in the air? Could this happen with water molecules? Yes. And so it could be in any liquid. Could it happen in a solid? Yes. And so again, want to emphasize, we are talking about this general idea of one molecule hitting another. It doesn't have to necessarily be what humans can hear. It doesn't have to be in the air. It doesn't have to be in the water. It could be all of those. And it could be in solids also, as long as one molecule hits another. Using the last chapter as our guide here, I would classify these as a longitudinal wave. In fact, you probably noticed that this is the machine I used to illustrate longitudinal waves. And so our starting point here is a very conceptual, as it should be, starting point here are what are sound waves. And that's what sound waves are. They are molecule hitting another molecule, hitting another molecule, hitting another molecule. So in the case of my voice, you all hear me. How? Well, I have vocal cords, right? And as I talk, I am making my vocal cords move, hit the molecules with a particular pattern. And that pattern then hits the air molecules with that pattern. And eventually each of those molecules hit another, hit another, hit another, and eventually that same pattern hits your eardrum. And so you hear the sounds I am trying to make. Again, none of the molecules from my throat and my voice get to you, so you don't have to smell my bad breath. You can hear my voice without the molecules getting there. And that's this idea. In fact, probably a good place to start is a little more visual, since you can't see my vocal cords. But what if I were to take this U-shaped object, we call it a tuning fork, and I were to hit it? You hear anything? Yeah. And so what is happening? Yeah, that little piece of metal is now moving. And so our sound waves here start with something moving, something mechanical, which then hits the air molecules, which then hits the next, and hits the next, and hits the next. I like to draw it this way. I like to say, okay, let's take this piece of metal. Here's my little handle here. And when I strike it, the metal is moving back and forth. Now, I guess the other piece is too, but I'm not going to focus on that one for now here. But as that metal piece goes back and forth, I'll put a little dotted line here, maybe to represent zero position. And I'll start my clock when it comes along and it makes its first push. And so the molecules that were here get shoved forward. They join up, if you will, with the molecules that were already there. And I'll represent that with a lot of dots, meaning there's a lot more molecules in that little clump than there would have normally been had I not started this tuning fork. And of course, once this collides in, they continue to collide into the next one. So this little clump of highly concentrated molecules keeps moving down. Now, meanwhile, of course, this piece of metal comes back and hits it a second time. And so this clump will have moved down to, say, here. By the time it makes a second push, and so this clump will now represent my second collision with them. Yeah.
Are the molecules moving back towards the tuning fork? What's hitting? When it vibrates back the second time, what's it hitting?
Oh, yeah, well, okay. So remember, okay, there would be molecules around here, and they're not stagnant. They are moving very, very fast, 700, 800 meters a second here. Well, maybe not quite that fast at room temperature, but 500 meters a second. So as soon as you pull it back, they rush in. A lot like you might say, what if I had a swimming pool and I took a cup of water and I pulled the water out of the way? What happens?
Then you still aren't moving molecules. Eventually those molecules will make it all the way down the line, right?
Not sure I understand what you...
So you move those molecules that little bit. The next time it vibrates, those molecules will move down a little bit.
Oh, well, maybe my picture was a little misleading here, because I do not mean this. I do not mean like a bullet from a rifle that you hit it and they just keep traveling. So these molecules, this clumping of molecules, are not the molecules that were back here. So what happens is the first molecules go like this and clump, but then they swing back into position and they swing again. So there's no net movement of molecules. Yeah. So this one molecule, if I was watching that one molecule, it gets pushed forward. As it swings back, it moves back. Yeah, okay, good. All right, now I understand your question. Yeah, but it's, yeah. So it's a wave, it's not a projectile. Right. And what I wanted you to see then is then later on, I would be something like this. Maybe I'll even put a fourth one here. And so here is my fourth one. And so these are my waves as they would be moving down. Let's make a graph out of this. What if I were to do the following? As I said, I wanted to draw a line down here to call this x equaling 0, and I'll do a horizontal axis here, x equaling 0. If I were to make a plot, and this plot would represent this wave, meaning this is the x-axis, this is space, if you will, and this vertical axis, I think might be a little bit hard to understand because I'm not going to be plotting motion of the molecules vertically. Do these molecules move vertically? No. They move what? Horizontally, right? So they're longitudinal waves. And sometimes that makes a plot difficult to understand because here's what I want to plot. I want to plot how far did they move away from their equilibrium. Maybe I should call this a delta x, right? Where did they go from their equilibrium? But I'm drawing it on the vertical axis, so I'm not saying that they moved on the vertical axis. In fact, to kind of help this out, you might say this is S. And I guess we could pick any variable, but your author chooses S. Say, look, where are these molecules? So the S really represents a displacement from their equilibrium position as plotted along the x-axis. But I think you can begin to see that right here, when I come back and I slam these forward, the molecules that are in this position, which you might argue are not in that position at that moment, but their normal position, their equilibrium position is here. The molecules that are in here have moved forward, right? So as they move forward away from their equilibrium, I'm going to put that number there. Does that make sense? Okay, good. Because then this grouping of molecules, and I probably should have given a little better spacing here. Well, those aren't exactly equally spaced, so bear with me here. But what I am trying to say here is these molecules right here, the ones that would normally be there, have not moved from there. Their displacement from their normal spot is 0. Well, these have moved over and gained with them. And so what I would have as I plot this wave, if you will, is that I have a displacement forward of these. These have not displaced, right? in between here, maybe I did give myself enough room. I'm going to put kind of an open box. Because at this point, I've talked about what happens when the metal goes this way, but what about when the metal comes back? Which really kind of leads to your question. These molecules then that were here got pushed forward. Then as the metal swings back, it pulls them back to this side. And so this point right here, if you will, the molecules that were here, which of course were created back here when this was swinging backwards, have now been moved the other direction. Or simply put, these molecules then are being forced. These molecules are being forced that way. These molecules are being forced that way. That's why I would say there's a bunch of molecules here. And it's interesting that where the bunch of molecules are crammed together in my pattern here would represent no displacement. That is because the molecules to the left and to the right are being squeezed into that location. And the process continues. Whoops, and I don't think I gave myself quite enough room to do this well. Bummer. But the same thing is happening on this side and that side. That I have then a pattern that is not well spaced or drawn. But I'm hoping you get the idea that I would have a backwards and forward motion. I would have a plot. That plot would have what shape and why? Yeah, what did we learn in chapter 15? You take a piece of metal, you strike it, it goes back with what pattern? Sinusoidal. So it pushes the molecules in front of it in what pattern? Sinusoidal. And so what I'm going to have then is a wave, if you will, a motion of these molecules. How would I write that down? And that's really what I wanted to convey. How would I write a wave here, traveling to the right, representing the displacement of the molecules in the air? Well, I guess I would say S as a function of x and t, right? S representing these molecules along the path. How far have they gone away? What kind of pattern would I have here? Cosine, right? If I call the beginning point where this metal rod has moved forward, it starts with a cosine function. If it's going to be a wave going to the right, how would I put it in my little formula? With a minus sign, right? There would be some angular wave number, which would be 2 pi over lambda. There would be some angular frequency, which would be 2 pi f, right? Lambda what?
The angular frequency, isn't that over lambda?
Angular frequency is 2 pi f. Yeah. And the angular wave number is 2 pi over lambda. In fact, where would the f come from? How would you determine the frequency here? Yeah, it is again back to 15. This is it. It's the period of oscillation of this, right? And so when I strike it, mechanically, it goes back and forth at some frequency. Now, without calculating it, we can easily measure it, and this one has been measured. In fact, it was hit, measured, and then stamped on here that when you strike this, it goes back and forth 1,024 times every second. So again, if I was trying to describe this sound wave mathematically, the first thing I would do is say, I know that frequency. Now I would have more to do in terms of what is its wavelength, but I do know this, that its velocity is its wavelength times its frequency. So if the frequency then is first determined by the mechanical motion of this, then if I knew the speed, I could also get its wavelength. And that's what we're going to talk about next. What are the speed of these waves and their sound waves? And so I'll build up to that. But that would give me that formula. What would go in front? Well, that would be the maximum displacement that it has. Notice again I used an S here. I know that we've been using up to this point an A, a capital A for amplitude. Again, just to be consistent with using the S here, your author uses the S. There's also another reason for that. I think even a better reason is we're going to start using the A, capital A, for area. And so, as you know, we've been using capital A for area and capital A for amplitude, but a lot of the problems we'll do in this chapter, we need both of those. So, to help avoid that confusion, we're going to get rid of the capital A for amplitude. Yeah, they mean S, yeah. They mean what is the maximum amplitude. Now, I write that on the board, and we'll do more math as we build up to it. But there is a second way of thinking about this wave. And that's where I want to get started. See, I have described it for you as what I would call a displacement wave. How far did the molecules move? But you will probably also notice then that the molecules are clumped together here, and you could call that then maybe a pressure wave. How much has the pressure changed from equilibrium? And so in that sense, it's a lot the same, except where is the pressure the greatest here? Yeah, right here we've got a huge clumping of our waves. And here, oh, I did a terrible spacing on this. Here they've moved away. Bummer. And I have a low point to my molecules. And the point I wanted to illustrate is we have another option here of writing this equation not so much as how much have the molecules moved, but how much has the pressure changed. And so when you're saying one, you're saying the other, because certainly it would still be traveling to the right. And certainly it would still have the same frequency and the same wavelength. So all of that is the same, but what would be different would be what? Yeah, and so it would be shifted. So if you want to look at this wave as a displacement wave, fine. If you want to look at it as a pressure wave, that's fine too, but you're kind of focusing on something different, and then the phase relationship between them is slightly different. And so your author kind of mentions that and says, well, look, then there's got to be a maximum pressure that it increases by. And how much does it change? And obviously then that would not be the same number. I mean, this is a number that represents how far did the molecules move. This number represents then how much did the pressure gain. They must be connected mathematically. Fair enough? And so in the interest of saving a little bit of time, let me give you that and say I think your author did a pretty good job. He's got about a 4-step proof there that says what is the connection between the pressure change and the amplitude, and he says it would be this. And I think the only thing new here that you haven't quite seen as we get started is the rho, although I know we've used it in past chapters. This is the density of the material, which most likely is air, but not always air. And so if you know one, you know the others. Yeah, and well, maybe I should put all those. And you've seen the v, but the v is the velocity of the wave, yes. And then this is supposed to be the omega. So this is the 2 pi f, where f is our frequency. In other words, the omega is the angular frequency.
And we're talking about the energy velocity?
Yes, definitely. Yeah. And so again, as I mentioned before, I don't like doing that, but I think we need to do that at times for these quick chapters, and so here it is, and I encourage you to go through the derivation so that you have questions about the V or the rho, you'll know what they mean. But I thought that would be a good place to start. And as we get started there, then notice then as we begin to talk about waves, this first sound wave that I had you listen to from this tuning fork was 1024 hertz. Could we have other frequencies? What if I picked up this piece of metal and hit it? Oh, that's terrible. Can you hear that one? Can you hear that one too? Are they making sound waves? What's different about them? Okay, and so going back to our mechanics, I hope you will see that this tuning fork is made out of material, same material, aluminum, but it's a little longer. It's also a little thinner. So what would you say about the rate of this one vibrating back and forth compared to that one? Yeah, that longer arm, that more rotational inertia, is probably going to mean this one will not go back and forth as quickly in 1 second. Now, it will still go back and forth. So will it still produce sound? Yes. In fact, this one was measured. It happens to be half of it, 512. And so we have 2 sound waves. But they don't have the same frequency. And so when you listen to sound waves and they hear different, you say it's a different tone, a different pitch. What are you really saying physically? Yeah, different frequency. So if I were to come over here and kind of make a little chart here and say, all right, now that we're starting to get a good understanding of what sound waves are and how I might describe them as a sinusoidal wave, either a displacement wave or a pressure wave, I can come over here and say then there is an infinite number of frequencies I could have. And so all sound waves really have the same basic physics. They are different in their frequencies. Some frequencies you would call a high pitch and a low pitch, but that's kind of that first part I want to get at. What you call pitch or tone is your brain telling you the rate at which the air molecules are hitting your eardrum. And so you may not be able to tell me that the molecules are hitting your ear at 1024 times every second. But I bet you could tell me that these two are not the same. And that one of them is doing it at a faster rate, and that's your brain picking up the pitch, the tone. And that's really kind of the lesson here, that sound waves come in all kinds of different frequencies, but they're the same basic thing. One molecule hitting another, hitting another. Your ears are built in such a way that they can pick up this range. This is what we call the sonic range. But again, to illustrate one more time, what do you think would happen if I picked up this piece of metal? And I think you can see this one is even longer. It's kind of hard to hear. Maybe you can hear it better there. Well, now I'm making the wood move, so I'm pushing a lot more molecules. Yeah. And so when you hear that one, again, you would be having those molecules hit your eardrums, but at a different rate. And this one, I believe, is half again. Yeah, 256. So I have shown you so far kind of in this category. The lowest one, the 256, we did a 512, we did a 1024. And all of those are within the hearing range of humans. That's the sonic range. I could go to lower and higher frequencies in there, and you would be able to hear them up to a point. Could there be frequencies less than, say, 20? Sure. Just because your ears are not designed to hear that doesn't mean there's not sound waves in that range. And other animals, I'm thinking of elephants in particular, are well adapted for hearing these lower frequencies. And so we have a name for this. Anybody know? Yeah, this is our infrasonic range. And likewise, the reverse is true. We can get up to really, really high frequencies. They can go beyond what humans can hear. But they would still be called sound waves. They're still the same basic physics. So just because we as humans can't hear them doesn't mean other animals can't hear them, such as dogs or particularly insects can hear up to really high frequencies, like 100,000 hertz. And so they got a whole hearing range that we're not privy to. We just, okay, well, there's sound there, we don't know. That's what makes dog whistles, I think, so neat. You know, you see someone with a dog whistle and it's like, did you blow the whistle? I mean, the dog comes running. But to the dog, it just, I mean, that's what it sounds like. But for the human, it sounds like, well, did you blow the whistle? Yeah, because it's up here at 30 kilohertz. And just because you can't hear it doesn't mean the dog can't hear it. I brought out this speaker purposely for this. I'll start with what I call the broken speaker. If you guys remember this one from 102, it's a big old speaker. We tore the paper diaphragm and ripped it apart so that we can illustrate that there is a magnet. There is a big magnet. I took another speaker that I didn't want to destroy too badly, but unfortunately had to destroy a little bit to show you, okay, there is a magnet in this one too. And they all have a magnet because they interact, and for those of you who went through 122 already will recognize this. This is a coil. You pass electricity through a coil, it becomes an electromagnet. For the rest of you, I guess we'll do that next fall. But if I pass electricity through this, and this is a magnet, and I already have another magnet over here, if you ever played with magnets, what happens when you bring two magnets together? Yeah, they push or they pull, depending on how you align them, and there's a push and a pull. There's a movement. And so in this case, this would take this paper diaphragm and either push it out or pull it back. And as we changed the electricity on and off, it would go push, pull, push, pull, push, pull, push, pull. Is it pushing on the air? So instead of being a piece of metal that pushes back and forth, it is a paper diaphragm that pushes back and forth. And that is generally how today's system works. If I take this little box, which sends electricity, it sends electricity at a rate that is determined by those knobs. And so in this case, I think you can hear the sound. The sound is 946 hertz. This paper diaphragm is going back and forth at that rate, hitting the molecules, which then hit your eardrums. If I change the dial, your ears will quickly pick up that it is now hitting it at a different rate. And in this case, you would say a lower rate, right? And the dial even says 639. If I go to lower settings, again, your ears will pick that up. 300. If I go to really low rate, it'll sound very low in pitch or tone. And eventually go beyond. Oh, that setting won't go that low. Let's try that setting. What's that one? 3? Ah, there we go. 3. And so is it producing sound? Yeah. But it would be in this category, I'm trying to say, is it infrasonic, and so I am producing sound waves. And it's low enough in frequency that I think you could actually now see it, where when it was at 900, it was just moving a short distance, going so fast, it at most looked blurry to you. But this one you clearly can see. If we run through the dial, well, we'll go to this dial I think will only get me up to about 20. Yeah, so there's 20, and those of you in the front may begin to hear it. Also, because I tore the paper diaphragm, the little pieces of paper shake at rates that are different than that, and that's often what people hear, you know. But if I go to some other settings, I think this one will serve me well. And go on through, we can hear these different frequencies. Here's around 500, 600, 800, and 1,000. And in the interest of time, maybe we better not spend too much time here. But it is kind of nice to notice the connection between the number and what it sounds like. Here we're only at 2,000, so we've got a long way to go. I'll switch over to the next setting, but looks like there's a couple of questions first, yeah?
So I can get the part that how it produces the frequency and the amplitude, but how does the speaker produce like the different sound from like a violin or guitar? Why does it sound differently?
Oh, well, okay, so obviously what I'm showing you now is the simplest case, the basic physics where it's just one frequency. If you then take a violin, the violin will be, when you play the note, it will be playing the fundamental note, let's say A, but it will also play a bunch of overtones. So there's actually quite a few different notes being played there. A and an octave above that, and an octave above that, and an octave above that. So a violin does not sound like this. But even a violin versus what was the other instrument you said? A guitar? But even if a guitar at the same note, A, their fundamental frequency would be the same. Even their harmonics would be the same, but the intensity that they play those harmonics are different. And so an A on a violin doesn't sound quite the same as an A on the guitar.
So, basically, it combines different frequency waves together.
Right. So our more complex sounds, like my voice, is made out of hundreds and thousands of different frequencies, all at the same time. And so this is just a simple case. I mean, who would want to listen to this all day? I mean, we just aren't accustomed to single frequencies and monotones. I mean, we like a variety of frequencies in humans. So when we play music, there's all kinds of different frequencies, and you know, some are more pleasant to the ears versus others, and yeah, some instruments are more pleasant to some people than the other. But that's really the key, is it's not just one frequency that we ever hear. It's a whole group of frequencies, and even if those frequencies here and here are the same, the intensity of the individual frequencies can be different, and that too can have a profound effect on our perception of hearing.
Is the intensity the amplitude?
Yeah, and I haven't got that far, but the intensity will be the amplitude, the movement of those molecules. That's our next step, exactly.
That's kind of where he was going off of, but say you have a speaker and you're playing at 1,024 hertz.
Yeah.
And then you rang your fork as well.
Yeah.
Would they be the same key? Like,
Yeah.
Would they be harmonic? So is 1,024 hertz always say E or A, or
Yes.
is it always a
Yes.
certain sound? No
Yes.
matter what instrument it was played on?
Yes. Yes, exactly. But then again, make this clear, when you play a musical instrument, unlike these tuning forks or this electronic box, these make just one frequency. When I play a note on a guitar, I've got that fundamental notes that I've read on my sheet music, A, but the guitar is playing A and an octave above that, and then double that, and double that, and double that. And then it's at different intensities, yeah. So let's see, I guess we were at 2,000. Shall we flip over the setting here? Here's 2,000 again. 3, 4, 5, 6, 7. Obnoxious frequencies in the 8, 9, 10. Gotta love this one. This is my son's ringtones. He just loves this one. The 13, the 14. Here? So some of you. And so you begin to notice that the human's ears begin to phase out. especially as you get older and older. If you can't hear that, it's bad. But getting up here, I don't know when bad would be bad, but definitely it fades away with age. In fact, I've seen medical charts that show pretty accurate predictions as hearing tapers off from age 8 on up. And so you don't usually think that it's as early as age 8, but it is. And so usually about the time you get, to be my age, you can't hear this 16,000 anymore. And it's like, oh, okay. So, yeah, I can barely hear it. You can hear it, but you can't hear it. Most of you can hear it. You have a 40-year-old or 80-year-old years here, no? So it fades away. And that's kind of that philosophy of those high ringtones. The idea was to develop a ringtone that your teacher or professor couldn't hear the phone ring in class, or your parents couldn't hear it ring, but you could, yeah. The reverse was also true, that there was a mall, I believe it was London area, that catered to the older population. So they had a lot of young kids, I'll say kids, but 20-something here, that hang out in the mall. 20s love to hang out in the mall. But to kind of chase them away and bring in the older crowd, they aligned the sound system in the mall to just kind of operate 24/7 like this. And it didn't take long before the 20-something crowd just was not around anymore. And the 50-plus crowd never noticed a difference. They just came in and shot more. And so I guess it works both ways there in the terms of selective hearing. And so those are our sounds. And the next step, as you already pointed out here, is I would ask this question about, okay, what about I'll say the loudness of it? I mean, watch, let's go back to one that is clearly hearable. This is a good one for 2 reasons. One, it's a little warning for next week. Next week we are going to do sound waves, we're going to measure the speed of sound, we're going to measure a lot of the properties. We're going to do this, and we are going to listen and measure to this sound for 20 minutes. Everybody in class. So be prepared. If that means bring a bottle of Advil, so be it, but be prepared. This is the one I feel I got to give you kind of a heads up and a little bit of a warning here. All right. So let me try a different knob here. Yeah.
When it comes to a distant travel, what travels further? Or is it all very similar? Ultrasonic, infrasonic?
Oh, okay. Well, I haven't got to speed yet. That's kind of the next thing here. What is the speed or velocity of all of these? But I'll just say it since you're asking. All the different frequencies travel the same speed. And unless something more complicated goes on here. But in general, they're the one. And that's part of this lab you're going to do. Because what I didn't say, and maybe I should just as well, is you do this for 20 minutes. You measure its speed. Then you do this for 20 minutes and measure its speed. And the point of this is to measure the speed of 2 different frequencies, and you will discover they are the same. And by extension of that, all of these frequencies are the same speed. So let me talk about that next, but what is the speed of these waves? Yeah.
I'm not sure if I misread the question, but it seems a little different from what he was asking, because that's more like speed, and I think he was asking about what travels farther. So it could still be, it could be different speeds.
Okay, so maybe I did misunderstand your question. I apologize, but I will say also, all the different frequencies travel the same speed. But as sound moves out, and you can imagine any organized pattern, it loses its energy. Right? It gets absorbed, if you will, into other forms. I shouldn't say lose energy, right? Because conservation of energy, you never lose energy. But it goes from sound energy into heat, okay? Which is the whole idea of why we put these soft foam boards up here on the top, so that as the sound waves go up there, the movement of those molecules make a soft and then make those molecules in there random and become heat. All right? So the question was, I have multiple frequencies, high frequencies, sonic frequencies, and infrasonic frequencies. They do lose their energy to heat at a different rate. So if I were to play music, say, over here in the corner, the high frequencies lose their energy faster than the low frequencies. Was that what you were after? So if you are far away from the source, and maybe you've noticed this, I know at my house there's a family that's about 4 houses up, and they like loud music. But all I hear at my house is the bass, exactly. And so as I'm in my driveway hearing their music, all I hear is this boom, 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 boom. What the heck are they listening to? You know, but if I go for a walk, and you know, then I can tell it's pretty decent music. I'm just so far away. All I get is the infrared, which actually kind of makes us full circle. You remember that I commented about the infrasonic and the elephants. This is the beautiful thing about a herd of elephants, is that infrasonic can travel miles and miles, and so a herd of elephants in Africa may not look like a herd, because you have one elephant here, and it could be another half a mile away before the next elephant, and the next elephant, and the next. And so these elephants can be spread over, say, 10 miles, but they can talk to each other because they communicate in the infrared, and it does not get absorbed like you and I if we tried to talk to somebody a half a mile away, and they can still hear that. And so that's the advantage of that low bass, that infrasonic. Good. Thanks for clarifying that question. It's a better question that way. All right, now back to your loudness. This is your loudness here. How are we doing on time? Oh, good. If I turn this on, I want to change a different knob here. If I do this knob, what do you notice?
Less loud.
Yeah, less intense, less loud. Fair enough? Same frequency? Okay, good. So I want to make sure that that is real clear. The loudness, the intensity of it is not based on the frequency here. The frequency is the rate at which those molecules go back and forth. I could kind of illustrate the same thing here by saying, give it a little tap. Still going back 1,024 times every second. Give it a hard tap. Still 1,024 times every second. It's just that the loudness of it, the intensity of it is different. And this little knob here, maybe you could actually see the behavior of this knob if I go to a low frequency that is visible with our eyes, but see that paper diaphragm moving back and forth? And if I turn this knob down, can you see anything different? Yeah, lower amplitude. The paper diaphragm does not move as much. The same thing happened here when I hit it soft versus hard. The amplitude is that. So the loudness, as you already asked then, is a direct connection to your ears picking up how hard the molecules. So there's two things going on here. One is the rate at which the molecules are hitting my ears, and the other one is the amplitude, or how quickly are they hitting my ears. And that's what my brain detects. My brain can pick up both of those. It can tell me what is the frequency and what is the intensity of the sound. Yeah?
What do all those buttons up there do? Do those like save frequencies?
Oh, they do lots of fun things. Oh, but see if we can even pick any of this up with our ear. And then we can start to get multiple frequencies. And in this case, we're back to the comment about musical instruments. This is not just one frequency. This is a complex mess of a lot of frequencies. And I better turn all that off, unless I forget about it when I turn it back. Not well with this. No. If I wanted two frequencies, I really need a second box. We can stack these together, and I probably should. I guess if I just want two frequencies, maybe. Oh, but you meant two at the same time. Yeah, that would be a good setup. I should get another one, and you'd be able to pick out the two at the same time. In the same way you heard a little while ago when I hit those two, you picked up both at the same time. Yeah. Okay, but there's the loudness of it. Next step. Velocity of these waves. Well, certainly keep in mind that the velocity of any wave is wavelength times frequency. If they were waves on a string, they were the square root of the tension divided by the mass density. I trust you remember that from the last lecture, and of course that's what we did the lab on. Although I guess a quarter of you still have to do the lab this afternoon. But that was to illustrate that the speed is connected to between that tension. In fact, what I put on the board last chapter and want to put on here again is that any set of waves would always be made up of an elastic property. How much does the material push back, but also on its inertial properties? How much mass does that particular wave have? In fact, while I'm writing this, I'll power on the overhead here for a moment, because when it comes to sound waves, this one is fairly easy to deal with. That one is what we would call the density. I guess I would write it this way. Rho. And that's that symbol right there. What is the density of this? If the material is more dense, that tends to slow it down. And of course, string waves, maybe I'll put them back over here so we don't confuse them, but if these were string waves, that's what we meant by the mass density. That's why you did the little experiment this week, or for some of you, you will do it today, was to illustrate that the speed of these waves does change with the mass density, and that's why you had three different strings. In this case, I'll just pull up a chart that your author has in this chapter. It's the table number 1 here, and point out, look what, as he writes this, hydrogen, what's the speed? Helium, what's the speed? Helium is 4 times more massive than hydrogen, right?
That's why when you inhale
Oxygen, which is mostly nitrogen. Nitrogen is what? About a 28 and 4, so about 6 times heavier than helium. And then oxygen is a little bit more than nitrogen, and so again, a little bit slower. Now, of course, that's not the whole story. The other half of this is the elastic properties, and so something else could be happening when we go from material to material. But the first basic thing I want to point out here, as clearly as they get heavier and heavier and heavier, they go slower and slower and slower. And yeah, you pointed out an interesting effect with the helium and the high voices when people play with helium, which probably not a good thing to do, but nonetheless it's kind of a fun thing to do. And that's the density of this whole piece of the puzzle. But what about the other part? The elastic property. Well, I'm going to put a word up here that you're not yet familiar with. So we won't do too much with it. Its symbol is a B. Whoops, that looks like more like a beta. But it's this. It is, how does the pressure change with volume? It's called the bulk modulus, but not worrying too much about the bulk modulus. So let me emphasize that. There's a lot of important things to learn for this chapter. The bulk modulus is not one of them, okay? But the idea of the bulk modulus is, what is the bulk modulus? Well, let's take a container of gas. What I mean by this is if I squeeze it, so I change its volume, Does its pressure change? Yeah, and by how much? You see, if it changes by a lot of pressure, that means it's ready to spring back right away, right? It has a large elastic property, huge spring back. So anything that has a large bulk modulus, anything where you squeeze it and it wants to come back with a large force, has what we'd say a large bulk modulus. And a consequence of that means it would have a lot of speed to the waves, because you go to hit them, they spring back right away. Something with a small bulk modulus, just you hit it and say, I'll go back, what the heck. You know, and they're not real enthusiastic about coming back here. And so that's the second property about any wave, is the combination of how heavy are they and how much they spring back. And again, I think you can see that in the chart here as we jump across from gases to liquids, especially to solids. Solids, you will notice their speed of sound is much greater than the gases. Because as you try to push a solid, it pushes back right away. I mean, it's, as the name implies, it's solid. And so these numbers tend to be greater than these numbers. And as we look down the solids, you'll see things that are kind of soft, like rubber and lead, have a much lower speed than the other materials that are hard and spring back right away. And glass is up there. Even though glass is brittle, people kind of miss the idea that it is hard. Glass is very, very hard. It's just also brittle. So if you get enough, hit it hard enough, the thing just kind of cracks into a bunch of pieces. But also notice something else up here. Back here in the gases, they listed air at both 0 degrees and 20 degrees. What did you notice here? Where does it travel faster? In the warmer temperature or the colder? Yeah, in the warmer. And so why do you think it would travel a little bit faster here in this warmer air? Yeah, it's less dense. They're warming, they're spreading out. If you know a little bit about the behavior of molecules, I brought this out. We're going to see this a lot when we get into thermodynamics. I know you saw it a lot in the Physics 102. What's the difference between something hot and something cold? Yeah, if I let this represent the movement of molecules when it is cold, that's the movement when it's hot. And when they're hot, they move really fast, they kind of spread out, they have less density, and they travel a little bit faster. Now, that's a little bit unfair, because it changes this too. And we're not going to dwell too much on that, but I am going to give you the results. And the result then is this, that the velocity will change depending on the air temperature. And keeping in mind then that for these higher air temperatures, as you can see in the chart, they go a little bit faster. So if I were to ask you, what is the speed of sound, you would say, what temperature? Exactly. That's the correct answer. The 343 is what? Yeah, 20 degrees. Rooms tend to be closer to 22 than 20 degrees. So don't be surprised if we use 344, 345 a lot, even 343. Seldom will we use 331. That would be the speed, you know, if it was freezing outside. But the general answer then, after a little bit of thermodynamics, which again, without proof, I will give you as 1 plus the temperature on the Celsius scale divided by 273. And so as we leave this section and get into thermodynamics, we could actually go through and derive this. I don't think time will allow us to. Probably somewhere in your education you might, actually I bet you will when you take your upper division thermodynamics and you come back and redo your thermodynamics here. But this is the result of all of that. And so I wanted to give you more of the concept of it. In fact, don't be surprised if you see this a lot. If we did a Taylor series on this, And now you might be happy that we don't have enough time to do a complete Taylor series on here. But as you guys, I think, remember from your math class with Taylor series, you would get something that looked like this. And so this is a common formula that you see a lot. 331.5 plus 0.007 temperature on the Celsius scale plus ... And then we just throw away the ... and say this is a pretty reasonable approximation for the speed of sound waves as the temperature changes. And so be prepared on the homework to do that. It actually makes it nice. You could either start with the temperature and get speed, or measure the speed of sound and get temperature. And that's what you're going to be asked to do in that lab next week. So after you make it through the obnoxious part where you got to listen to those sounds all the time, you will then be asked to heat up your sound tube, measure the speed, and tell me the temperature of your sound tube. And then the reverse, you'll cool it down and get the temperature. And so we'll use the speed of sound as a temperature probe in the lab next week. Okay, and so it does change. And I know you have a number of homework problems that will ask you to either find the temperature or find the speed, or need to know the speed in order to answer the rest of the question, but they don't give you the speed directly, they give you the temperature. Also, I guess I should point out that if they don't say anything about the temperature, feel free to assume it's around 20 degrees and that you can use 343. So that's kind of the general rule. They say nothing about temperature, they're implying room temperature, use 343. They say something about the temperature, use their speed. Well, I'll keep going here, because another issue or set of issues that we should mention is, what is the power in a sound wave? Here's a new word. What is the intensity or loudness? I guess actually we kind of mentioned that already, at least in the word. We haven't given it a formal definition in the equation here. And what is sound level? And in fact, intensity and sound level are really close to the same. So much that I think people often confuse them and say one is the other. They are slightly different. And so hopefully I can pound that out here. I'll go with power. Power, as I think you already know, is energy per time. How much energy is in this sound wave? In other words, if I had a speaker right here, and I were to turn it on, I won't turn this one on again so you won't have to listen to it, but the sound would go out. And it would go out in all directions, and it would be three-dimensional. I can only draw it on the board kind of two-dimensional here, but as it would go out, if I had a certain amount of power in this wave, oh, why don't I just say, this would be a lot of power, but I'll say 1 watt. And I should say a lot for sound wave. Obviously that's not a lot for a car or a light bulb, but for sound waves, as we'll see in a moment here, that's quite a bit of energy in a sound wave. It's also why, if you guys remember back in Physics 121, when we did our conservation of energy, and a lot of times we said, oh, we have a collision, and after the collision, some of the energy is kinetic, some of it is heat. And usually somebody says, well, what about sound? And I usually say, it's too small, we don't need to worry about it. But there is a little bit there, and we're going to see that sound waves do have some energy, but really very little. Your ears are amazingly sensitive to a very, very small amount of energy here. But if I had 1 watt, what's going to happen is that will flow outward, and now that energy is spread out over a bigger area. Fair enough? But it's still the same energy, isn't it? It's still 1 watt? So if you're interested in the total energy, then talking about its power is great. But that's not usually what we are interested in. What usually happens with sound waves is they come into a detector. The detector has a small size. Maybe it's a microphone or maybe it's your ears. I'll switch colors here, but if I were to put kind of a small little opening to a microphone or an eardrum there, I'm not really interested in how much energy total is in the wave. What am I interested? How much gets into my microphone, right? I'm interested in the energy per area. Because if I were to put my microphone out here, and as I get further away, what do you probably notice as you get further away? Does it sound just as loud? No, why not? Yeah, it's less energy in that one little spot. So we need to be careful here when we talk about power versus intensity, because the intensity is all this power per area. Power per area. There's that capital A. That's why I was saying let's save that capital A for area. And so there are times where the intensity is far more interesting to us than the power. In fact, I might even go on a limb to say I think most of the time when we are dealing with sound waves, we are more interested in the intensity of the sound, not the power in there. I don't care how much total sound there is. It's how much got to me in my eardrum, how much got to my microphone to record it.
Does the sound always travel in perfect sphere?
No, I mean, not ideally, but if there was nothing else around and I made something kind of uniform, then it would go in equal directions. We're going to assume it goes in equal directions. But if I stand up here with my voice this way, a lot more sound goes this way than that way. Yeah, especially if you have one of those yelling cone things, right? And even the sound that does go that way ends up bouncing off this wall and coming back that way. So people who are 3 meters that way hear a lot more sound than people who are 3 meters that way. It hits the wall and comes back.
How do you define area? Just the area of a circle?
A sphere. Remember, yes. So in the simplest case, I would be saying this is that 1 watt divided by 4 pi r squared as it goes out. If these were water waves, in fact, that's the homework question you asked me about the other day. If these were water waves, then they would not be on a surface. They would not be spread out on a sphere, but they would be spread out on a circle. And so this would be a 2 pi r. That's how we got the amplitude for those water waves. And that was last chapter homework, right? That was a 16 homework, not a 17?
Right.
Yeah. Because sound waves travel in 3 dimensions, whereas the water waves don't. And the sound level, and the whole reason why it can be easily confused with intensity is because it is a way of representing the intensity, but it's probably best to represent it as what I would call a relative intensity. Let me explain and do some more math here. I think the first one, the power, is pretty straightforward. We've done power many times. Probably don't need to say too much more about that. It is, again, as I was trying to illustrate in this picture I just erased, it is all the power on that whole wave, and as it spreads out, assuming it doesn't lose any to heat and absorption as we talked about before, is that same energy now is spread out over a bigger area, but it's still the same energy, same power. So 1 watt, 1 watt, 1 watt. But the intensity goes down. And so what I probably want to look at is more of this question. What would be the equation and what would represent the intensity of the sound wave? Remember, this is the power per area. And I guess what I mean by this is if we go back a chapter to a string, and again, we were just low on time, so we didn't derive this equation. But do you remember that question about how much power goes down a string? Do you remember the answer we got? Had 4 variables, had a 1/2. It had the mass density, you know, kind of makes sense. How heavy is this string? I mean, that's part of how much energy flows down the string. Yeah, there was a V, kind of made sense. How fast is it flowing down? What else was in here? Yeah, and amplitude squared. And so again, without much proof but a small discussion, we said if you just took a string and you were to shake it like this, energy would flow down there, power. Now, since it's just a string, it would not spread out. So we never asked the question, what's the intensity? It wasn't important. But now with sound waves, we really are more interested, not in the power, but what is the intensity. So what if I took this equation that was valid for strings and changed my symbol a little bit? And here's why I want to change my symbol. What does this A stand for? It's amplitude or area?
In the new equation.
Right, so in the string it was amplitude. So as I get into this chapter, will it be okay if I do this? And so let's make that change now. It's the one we discussed back here. It'll help me from confusing A for area now with amplitude, okay? And so again, if you're dealing with strings, go ahead and still call it A for amplitude. That's very useful because we didn't worry about the waves spreading out. But as we get into this chapter and we change the symbol, this would be the equation, right? So when I go to calculate intensity, wouldn't intensity be power divided by area? And so again, maybe to make it clear, I want that A to represent area. That's why I switched it here. So this would become a 1/2, a mu, a v, an omega squared, an s squared for amplitude divided by A for area. And I just wanted to make sure you weren't going to cancel those two off. This is amplitude, this is area. Let's give it a different symbol for just that reason.
Are you going to replace mu with rho?
So now you see where I'm after. This makes a nice, simple, easy step here. What was mu? Mass per length. So now if you divide that by area, you have mass per volume. You have density here. And so our little equation for sound waves is what I was after. And so again, taking our formula for the string, changing the symbol A to S, dividing by area to get intensity, this will help us a lot. This is what I was after. This is the equation for what is the intensity of sound. In fact, I think I even used that as an example yesterday, even though we were talking about the power on a string. I think I used sound waves and a tweeter and a subwoofer as an example, and those are really sound waves, and so it wasn't really appropriate for that chapter, but you can see by extension it's the same thing, that you have the power determined on the square of the frequency, the square of the amplitude, the velocity of the wave, and of course the density of the wave. How much do these molecules weigh as they kind of push through? And so this whole idea of intensity, hopefully it's kind of sinking in. It's related to power, right? But it's not the total power. It's the power per area. Right? What would the units be? Well, what units would I use for power? Watts. And for area? Squared meter. And you might be happy to hear there's no fancy name we're going to give to this one. This is just it. These are the units for intensity. It is just the power, watts per square meter. How much energy per square meter. So I think that one is, I'm hoping it is fairly obvious. Yeah.
What unit is decibel?
Notice this is not decibels, right? Let's go to the next step. What's this? What is the definition of sound level? And as I was saying, it is very easy to confuse intensity with sound level. And you're already on that road because you want to use decibels. Decibels does not measure intensity. As we'll see here, decibels measures sound level. And so sound level is connected to intensity. All right. It is what I would call a relative intensity. In other words, if I take the intensity of the sound, so this I standing for intensity. Oh, I don't think I used the symbol I. Did I? Did I? Okay. All right. So if I use the symbol I for intensity here, in the numerator I'm going to put intensity. But at the bottom, I'm going to put what I will call a reference intensity. And so you can see that this ratio doesn't really give you the intensity, does it? It gives you what? Right, a ratio. It gives you what is your intensity compared to a reference, right? In other words, if this number was a 10 and this number was a 2, when I take the ratio, it's 5. What you're really saying then is the intensity I have is 5 times more than the reference. And so what we like to use for our reference is what we call the threshold of hearing. We like to say this is the minimum amount that a human needs to hear. And human ears are quite sensitive. You only need about 1/1,000,000th of a watt per square meter. And your ears would say, hey, those molecules are moving. I can pick that up. And so sound level is a way of describing how loud is that sound compared to the minimal amount of sound I can hear. Does that make sense? Now it gets a little harder than that. Question, David?
That's not quite the same as like a 1,000-watt sound system.
No, the problem with first of all, 1,000 watts, that's the total power. Doesn't tell me how much goes to my ear. Which kind of makes sense, because how much goes to my ear depends how close I am to the speaker, right? Because I could have a 1,000-watt stereo system and be a mile away and go, that's not powerful. The other problem with that is a 1,000-watt stereo system can be very misleading in the sense that it's consuming electricity at 1,000 watts. It's not producing sound energy at 1,000 watts. And so it may be only making 10 watts of sound energy out of that 1,000 watts of electricity energy it's consuming.
It's also spread out through multiple speakers, right?
Of course, and then it's spread out to multiple speakers and then spread out through the air depending on how close I am. So this could sound really loud if I am close, but it may not be very loud if I'm far away. Yeah.
Could you still damage your ears with an infrasonic or an ultrasonic sound if it's not high enough intensity?
Yeah, because the damage is coming by the movement of those molecules, and they're actually hitting your eardrums. Just the problem is your eardrums, as it gets to your nerve and the whole inner ear movement of the 3 bones and the little hairs, don't respond to it, but it's still pounding your ears. Yeah. There's been a number of tests, especially in that infrasonic, that you can make body organs vibrate at like 6.5, 7 hertz. So, they've been able to make people unconscious and, putting this sound speaker really loud at 7 hertz, and your liver kind of explodes and, you fall down dead. You never heard anything. Probably feel the pulsating inside of you, but yeah. So there's been a lot of, experiments with, is that useful for security, law enforcement, military applications? So I know the Navy has made some incredible guided sound systems where they can take, and this is audible in the ears, but they can guide high energy beams of sound to the point that you're in pain, you can't function, with the idea that a terrorist attack would be diverted. And a lot of this was implemented after that bombing of the U.S. Cole, and you know, because that boat just came right up to it. The only alternative they have was to either shoot the boat completely out of the water or let it approach the boat. But now they have these non-lethal approaches, where what we could do is we could aim this beam at it, and the captain of that boat will become incapacitated. So we don't have to kill them, but they also can't get close to our boat. Yeah. All right, so where was I here? I was trying to give you a good understanding of what sound level is, and how sound level is not the same as intensity, related, and can be confused. And it gets a little more complicated here, because not only is it a ratio, but it is the log of the ratio. And the reason for that is, again, back to you, the power in your ears. Your ears are amazingly dynamic, and what I mean by that is they can hear something as little as this. But even when it gets as high as 1 watt per square meter, which we often refer to as kind of the threshold of pain, this is where it begins to hurt. It's so loud. But that's 1 trillion times louder than what you could first hear. And so your ears are, like I said, really dynamic in the sense that they can hear really, really faint sounds and keep working just fine 1 trillion times more and still function okay before they start to feel pain. And so that's what's nice by having the log then, because when you take a log, you're just looking at the exponent. You're looking at it's 12 times, not 1 trillion times. Now, for whatever reason, maybe to make things look a little bit easier and give it a bigger scale, instead of going 0 to 12, it's nice to go from 0 to 120. So we put a multiplication factor in there. And so simply put, this is the equation for the sound level. The sound level, again, let me emphasize, that's supposed to be a beta, is given the symbol beta. Beta sound stands for our sound level. The conceptual idea is it's a relative intensity. It's how much is the intensity compared to a reference. It's a log function, and so some of these things that spread out a lot, we like to use log functions on here. What are the units then that we use for sound level? And that answers right your earlier questions. This is measured in decibels. The symbol, a little d and a capital B. If I call up your second chart, you'll kind of see what the author has here for chart number 2, where it says, let's look at some of these. Because it is a log function, it can get a little misleading, because every time we go up by a factor of 10, right, here, and so if we go, well, let's say this number is, well, maybe I should ask, what would this mean to you if the decibel reading, the sound level reading, here was 1? Excuse me, 10. No, 0. There, confusing myself. 0. What does 0 mean? Do we have 0 on here? Yeah, 0 would be the threshold of hearing. Here's what you're saying. You were saying if the intensity of the sound is this small, which is the same as our reference, that ratio is 1, right? What's the log of 1? 0. And so 0 becomes our minimal amount of hearing on our sound level scale. And as the sounds get a little bit louder, the numbers go up, and what is often considered 120 decibels for our sound level, that is the threshold of pain, they like to say. And of course there are sounds louder than that. Nearby jet engine is listed up there at 150 decibels. I love this little guy, partly because it's little. But how much energy is really in 120 decibels? Is it a lot of energy?
No.
It's really not a lot of energy, is it? 120 decibels would mean what? Well, this is 120, right? Divide by 10, that's a 12. Well, that means this intensity is 12 in the exponent compared to that one. So there it is, right? It's only 1 watt. 1 lousy watt is the threshold of pain. This nice little speaker is 120 decibels. And it's just a little baby speaker, right? It's not much energy, but it is 120 decibels. I better not do that a second time. But it is loud. But loud is not much energy. Yeah?
Does the reference intensity change based off what's picking up the sound? Like say if you have a recorder,
what?
Is it the same number? Is it 10 to the negative 12?
If I had a what?
Like a recorder.
Oh, well, okay, now, and we can do fancy things, but for this chapter, I'm talking about sound regardless of how it gets recorded, okay? So I would say the reference does not change. This is kind of the standard of, this is what humans, and no humans are the same, so some obviously can hear lower intensity sounds and others can hear higher, but apparently on average, this is kind of the given that humans can detect. So I would say the first part of no, we don't change the reference, but keep this in mind because you will see that same equation in many other venues. For example, my home stereo system does list on the dial decibels. Now, I need to be careful because that stereo system is not trying to tell me the decibels of the sound level that it's producing. Not at all. It couldn't do that anyways because it would depend on how close I am. So it's not trying to tell me how loud the sound is. What it is trying to tell me, though, is that there is the electricity being produced by my knob in reference to something. For better or worse, mine uses a reference of full volume. So when I turn the knob to full volume, that ratio is 1, I get 0. So when my stereo system is on full volume, it says 0. Everything less than full volume now becomes negative. And so it lists my levels as 0 down to negative whatever.
So it kind of depends on what you want to read.
Right. So I guess what I'm trying to say, for us, this will never change for sound, but this same idea is applied to electronics. It's applied to earthquakes and geology. The Richter scale is based upon this. So there's a lot of other useful examples of this. Yeah, and the Richter scale uses as its reference the smallest movement that they originally could detect. And so if you get something like an earthquake of a 6, that means 1,000,000 times more movements than the smallest they could detect, right? Yeah. So they use that same idea. It is. It's very. How are we doing on time? Oh, good. We're cruising right along here, just about right. All right. So that's the idea of our sound. Well, one more set of things here. They kind of go together. It was an idea that was first discovered by a guy named Doppler, so you can imagine we call this the Doppler effect. I might as well put in here Doppler effect and shock waves because they really go together. If I was trying to describe it to somebody, the Doppler effect, I would say this. It is your perception or your observation of a shift in the frequency because of some motion. The shock wave is a continuation of that. Since a shock wave, as we're going to see, happens when you go faster than the speed of the waves begin to overlap. And so applying the idea of the superpositioning principle is the waves kind of just build up on each other. I'll start with this little diagram. Your author does a good job here of saying, what if there was some motion? I think he starts here, and he says, let's say that this truck is producing some sound. Maybe it's a horn. And as it's producing some horn, this rider is riding to it. Now, you can imagine if the rider was not moving, then the waves would hit it. Let's just say this is the horn from the car. Oh, that's a little high. What does the horn sound like? I don't know. That'll be the horn.
Sounds like that.
No, what is that? I don't think I'm going to. Oh, you want to hear a horn? No. Oh, no. Okay. All right. But for this, we'll say this is the horn. Now, I have it set at 461. Now, what that really means is you sit in the room, 461 waves come towards you. But what if you were moving towards it? Like this bike towards the car.
Double.
Wouldn't you pick up more than 461? Now, don't get me wrong. Is this still vibrating 461 times a second?
Yeah.
Yes. But what you would perceive, what you would hear, and that's this whole point, you're going to perceive, you're going to observe a different frequency than what that horn is actually producing. You're not going to perceive 461. And in this case, moving towards me, you would be more than that. Now, how much more than that? Exactly, it's connected to how fast you're going. And so the perceived frequency is a function of velocity. So velocity can lead to what I perceive, or perceived frequency can lead to velocity. And that's the neat thing about a Doppler shift. You might actually be a little more familiar with the word when you hear things like Doppler shifted radar. It was all over the news this morning, right? Because finally, looks like we're going to get some rain. Not much, but and rain once a year here, huh?
Rain last week.
That was rain. I think was it even measurable?
It was like a
0.2 inches.
0.2? So, it was measurable. Okay, all right. So we got 0.2. Yeah. So, yeah. God, they're talking someplace in the state, they're not even going to deliver extra water to the cities. And it's like, yeah. Fortunately, we live in an area where kind of, our mountains get enough rain. We're kind of self-contained, but we don't get some rain soon. Then it's going to be very, very problematic. Anyways, sidetracked here, but that Doppler radar was all over the news because of the rain. What are they doing with the Doppler radar? What is the intent of the Doppler radar? Whether it be for weather, or whether it be for traffic control, or whether it be for military applications, what's the idea? You send it up, you get a reflection. If the frequency shifts, what does that tell you? It's motion, and you can find out which way it's moving and how fast it's moving. Exactly. And that's what you would perceive. Let me ask the other way. What if the biker was going the other direction? Okay, you would perceive a different frequency, in this case lower than 461. Actually, I think this animation does a really good job of showing it. Let me switch to Don's little animation. Where's our web page? Getting closer. Oh no, that's it. Here we go. No, that's YouTube. Here it is. Doppler effect. Here we go. All right. So I'll start here. Here's the sound. Here's the speaker. Diaphragm moving back and forth, making waves. Here's the ear. As the waves travel across, it'll flash red every time a little pulse there. Flash, 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 right? So let's say this is our 461. But if this observer, not to be confused with source, observer, source. Okay. If this observer were to move towards the speaker, notice the flashing would be a little faster rate. What happens when the ear moves away from the source?
What happens if it travels the same speed? Does it not move?
Ah, yes. So that perception of your frequency can change. And that's what I'm trying to say here, conceptually. We'll do math in a minute here. But this would be the conceptual idea of why there would be a different frequency. And it gets even more interesting. What if it was the other way around? What if the source was moving? See if this next part in the animation helps. We're going to have the speaker move towards the ear. Of course, then it'll go past the ear. So watch also when the speaker is past the ear, moving away from the observer. So if I click here, and the source is moving, what do you notice right away? They bunch up here and spread out over here. So what does this ear perceive right now? A higher frequency, as if the source is moving towards it. What does the ear perceive now as it is moving away? A lower frequency. Now I would say that it is for a different reason, but when things are coming together, whether it's the observer moving towards the source or the source moving towards the observer, there is a higher perceived frequency. Now, the reason is a little different, so the math will be a little different, but either way, you will get a higher perceived frequency. And if they're moving away from each other, you will perceive a lower frequency. Now again, for different reasons. So the math will be different, and that will mean we got to keep track of whether the observer or the source is moving in our calculations, but nonetheless, the conceptual idea. Now, I couldn't have you move, but I can have the source move. That's why, if you were wondering why this thing is on a long wire, is so that I can spin it. And if I turn it on to, are we still at 461, and I spin it, you will hopefully hear slightly higher than 461 as it is moving towards you, and slightly less than 461 that is moving away. And how much depends on how fast I spin it. Right? And so those do change. And so the last part of this chapter, I think this is the last part. I should check here with my notes. Oh, I got to do a shockwave still. Hang on. So maybe I'll leave that on there for just a second. But let's do the math for this Doppler effect. Yeah? And so if I jump over here and say, all right, let's start with the case where the observer is moving. I think that's the easier one. And say, what would the observer hear? And as you guys already pointed out, conceptually, they're going to hear a louder one if they are coming together. I guess I would do it something like this. If I make kind of a little circle here and I put S. S for the source. This is the speaker system. It's moved off the screen there. But S for my source. And then I'll put another little mark here. Observer. And at this point, let's just say the observer is moving towards the source with a velocity of V sub O. Did you catch that? I'll ask it. What's V sub O? Why not V?
Because the speed of the source too. The speed of the wave.
Speed of the wave. Don't confuse the V's here. We're going to have 3 before this is over. Speed of the wave, speed of the observer, speed of the source. Okay? Easy to mix those two. And so right now, let's just deal with the V of the wave as VO, the observer, is moving towards it. Now, if there was no motion going on, I would have said this. The frequency, the real frequency, not the perceived frequency, the real frequency is the velocity of the wave divided by its wavelength. Fair enough?
Yep.
That's from last chapter. Okay. However, if the observer is moving, there's going to be a different frequency. Let me call it AF prime. That's what your author uses, so I want to use it. But don't think that I'm taking a derivative, okay? This is not, I'm not representing a derivative. I'm saying this is a frequency. That's not the real frequency of the speaker, but it is what is going to be observed. What would be different here? As I move in, will the wavelength change? Will the spacing between each of these be any different? No. That's going to be the same. Yeah, but I think you can see the velocity. The idea of the velocity here is that, wait a minute, these waves that are now coming towards me would be as if I wasn't moving and they were coming a little bit faster, right? And so that's why I'll put a little plus sign. And I'll put a plus sign because I'm saying I am moving towards it. What if I was moving away? I would have put a minus sign here. So let me put a plus and a minus. The top sign up here because it's towards the source, and a minus sign because it is away. So I've got two options. But again, you can see that the frequency would be perceived. Now, to write it so that it matches what the original frequency is, because the way it's written right now, I don't have the original frequency in here, but I could write the wavelength as the velocity of the wave divided by the frequency, the real frequency, not the perceived frequency. And so what this comes out to be is the perceived frequency then is this. Right? The perceived frequency is the original frequency changed by some multiplication factor that depends on how fast your observer is moving and whether it's an increase or a decrease. Fair enough? Well, let's try this. What if it's the other way around? Let's go back to our chapter here. Because I think your author does a pretty good job in this diagram and says, what would the waves begin to look like if the source was moving? In fact, maybe, actually now I think about it, maybe Don's animation was even better here. We got to go back to there. Is there a pause? Because I'd like to pause it right about there. Yeah. Okay, but whether I'm looking at the one from the book or Don's animation, here's the big key I wanted you to see. Right? This was our argument that, again, when the source is moving, then you would have a change in perception also, but for a different reason. So the math comes out different. And so let's run through that math here. Let's take this same little diagram here. Let's say, okay, here is the source. The source is producing waves, but as the source is moving, let's call this V sub s, velocity of the source. And for discussion reasons, let's just leave our observer non-moving. Of course, the reality is we could have both moving, right? We could have this truck that's honking its horn moving towards the bicycle that is riding and moving, and so a real problem is going to have both the source and the observer moving. I think your author has another good one. It's got a bat flying through the air, chirping, reflecting off a moth who's flying away for its life. And the bat is going to pick up a shift in frequency that is based upon its movement and the moth's movement. And I always find it amazing that a bat can then pick up that shift in frequency, know exactly how big and where that moth is, hunt it down and have dinner day after day. Or fly into a cave where there's no lights and just fly through a cave and never crash into the walls, and even know that there's 1,000 other bats right there, but there's just enough room for me right there. Tweet, 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 tweet. No light, no sight, but there's an empty spot for me to hang for the night. Or day, I guess I should say. Right? And so that's all based on the shifting of the sound waves and the reflection of the sound waves. So trying to apply this last equation here real quickly, I would kind of do the same thing. I would say, what frequency do I perceive? Because the source is now moving. Well, if I start my discussion with the original frequency is the velocity of the waves. So the waves are kind of crunched together here and spread out back here. But the original frequency coming from the source is the velocity of the wave divided by the wavelength. And it's kind of the opposite of what happened over here. Over here I said, did the wavelength change? And you said, well, no. But over here, did the wavelength change? Yes. Did the speed of the wave change? No. So the numerator stays the same in this case because I still would get these waves coming to me at the same rate. I mean, once they leave my source, it has nothing to do with the speed of the source. What has happened then is the wavelength has then decreased by a small amount, I'll call it delta lambda, if that source is moving towards me. What if that source was moving away from me? Then it would increase. And so again, as I do my math, I got to pay attention. Is it coming towards me or is it away from me? Is it the source or is it the observer that is moving? Or is both? Right. And so we'll put this both together here in just a second here. If I kind of rearrange this here for a second and put this minus and plus, and notice I'll try to put it in the same order. So in other words, the sign on the top part will be when I'm moving towards it, and the one away. Towards it and away. So it's the same order there. As I move, say, towards it at this point, I would say it has shrunk in wavelength, but by how much? Well, depends how fast the source is moving, right? But it's one wavelength, so what this diaphragm is going to do is it's going to produce a pulse, move forward and produce another pulse, right? How far did it move forward during those two pulses? Well, I guess that would be the velocity of the source times the period, right? How much time is there between each pulse, right? V times t, that's the distance you would travel. Now, simplifying this equation, we can get one that kind of looks like this. If we take V and then we do something like this, I will replace lambda with V over F. That is the velocity of the wave divided by the true frequency of the wave. I'll leave the velocity of the source alone here, but the reciprocal of the period of a wave is its frequency. That has a common denominator. And I'll group it together. And now I can get what I'm after. What is the equation for the shift in frequency? Would be that. And so I get, again, a slightly different equation because of slightly different physics that is going on depending on whether the source or the observer is moving here. If I put the two together and say, well, what would happen if both of them are moving? Well, then I guess I would say there would be a shift because of each of them. And so I would take the original frequency and multiply by the factor that shifts it, and then I would take that and multiply by the factor that shifts for the other reason. So I would have both those factors, right? So the total combination when both are moving would be this first factor. This is how much the frequency has changed because the observer is moving. And then it would shift by this much because the source is now moving. And so that would be the combination of both effects. And it simplifies a little bit in the math. There is an V on top and bottom. So when I deal with both movements, I get this. And that will be the box that I will put around saying I can get a total shift because of the movement of each of them, and then this is what the observer will get. Yeah?
In all those cases,
Yeah.
F prime is what the frequency that what the observer is.
Right, right. Yeah. So the F prime is the observed frequency. And I'll say it again, it shifted for two reasons. And they're slightly different. That's why they show up mathematically different. They show up because of the movement of the observer. They show up because of the movement of the source. Okay. And so that's our Doppler shift. And it looks like I won't have any time to do examples for you. So let me give you a hint on a hard one. What if we go to that bat problem again? Bat chasing moth. Which one is the moving? Which one is the observer?
Well, you said the moth was...
Which is the source, which is the observer?
The moth's chirping, right?
Right. This is a harder problem because I would say, from the bat's point of view, it is both the source and the observer, right? Now, I would say also the moth is an observer. It's not a source. It's trying to hide. My crazy neighbor, he loves playing with the moss. The bats come out at night, and we've got all these moss in the oak trees. So at night, they come out of the canyons all the time, and all these moss are all over the place. And you hear these chirp, 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 and the moss just beeline it back into the tree, hide. There's always a dozen that don't catch on. And they're just kind of floating around, and the bats just come by, snags. They're the first ones to go, you know. But my neighbor will go out with a tennis ball, and he throws it up there, and I guess it gets an echo out there because the bats just dive towards that tennis ball, and they get about this far from the tennis ball, and they realize it's not a moth, and then they zoom off the other way. But it's just kind of neat. They kind of chase these moths around here. But here's what makes this problem hard. Here's my warning for you is if the question asked, what frequency does the moth hear? It's pretty easy. You start with the frequency coming from the bat. The bat is the source, so how fast is the bat traveling in what direction? Okay. The moth then is the observer in that case. And so how fast is the moth flying and in what direction? Okay. And you would get the perceived frequency of the moth. But now what happens? Then that reflection comes off the moth. So I would say the moth is the source now. As it goes back to the bat, which is now the observer. So you need to do this calculation twice. And each time you do the calculation, you have a source and an observer. And the roles of the source and the observer switch on reflection. And so be prepared to do this one twice. That's usually what hangs people up. They just do the first calculation, but all they've really done is calculated what frequency does the bat pick up. It's the same way if you like to use those little sonar guns for measuring like baseball pitches. You know, you get the pitcher out there, they wind up, they throw, you got the little sonar gun out there behind it. It sends out a pulse and it reflects off the baseball. There's going to be a shift in frequency that the baseball perceives. But of course, what really matters is the perception that the gun receives when it gets back. And so then you got to do the calculation again, and then to put it into your electronics, and then of course hopefully have the display, the pitches, you know, certain amount of speed here. So there's that extra reflection there. And so that's what I ran out of time to do example for you, but that's the one I wanted to really warn you about, that one there. Yeah.
So when sound energy travels, although it's losing its energy as it dissipates, its velocity isn't decreasing.
Correct. Correct. And I know that might be a little bit hard to digest at first, but remember, this is not mechanics. These are waves. There is not mass that is traveling. And so when it comes to like a baseball, its kinetic energy is related to its speed and its mass. Okay? But in here, the energy of this wave is really related to how much the molecules move and vibrate. And they just collide one into another. Ding, 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 ding. Yeah. So they keep going the same speed, regardless of whether they have a lot of energy or a little energy. It's not a one, you couldn't use 1/2 mv squared is what I'm getting at. Well, the last thing, and there's a little step in math, if I think we have just enough time to throw it out. Fortunately, it's a fairly simple one, and that's this next part of this, which I've erased. What then is a shock wave? And you brought it up, the next part. What would this picture look like if you went faster than the wave itself? And you can begin to see now that if you went so fast that this began to catch these waves, then you would have an overlapping of waves. You would have what we called in the last chapter a superpositioning of those waves. The whole wave is a sum or a combination of the overlap of the waves depending on how they overlapped. And I think this other animation shows that really well here, where we start off here by saying, let's take a look at an object, this happens to be a plane, going subsonic, meaning slower than the speed of sound. And the waves that would bounce off of its nose would be crunched together here and spread out there. That's exactly what we just got done talking about. That's the pattern you have. That's a Doppler effect. That occurs when you're going less than the speed of the waves. But when you go faster than them, as this one is trying to show, you begin to see that you're making waves in the pool of waves you already made. So the net effect is the superpositioning of all of those waves. And so this next one shows what we would call Mach 1, Mach rated to how many times more than the speed of sound. This is exactly at the speed of sound. Every wave you make is right on top of the one before it. And so what you do is you get a buildup of huge pressure right here. And that then is not quite the same as, you know, the sound getting to somebody. This one is what I really want you to see. This is a little bit faster than the speed of sound. What you begin to see is you have a buildup, a superpositioning in kind of a V shape. It doesn't matter how many times faster than the speed of sound you go, you will still get a buildup of these waves, a superpositioning in kind of a V. It'll be a more narrow V, but you'll still get a V. Mach 2. Oh, I thought that last one was Mach 2. Was it? Oh, this is to give these to the math. Okay. All right. And so if we draw a little diagram here, here's what we will see. When the plane was back here, it made this wave that went out to there. So this distance would be v over t, v being the velocity of the wave. This distance would be vs sub t, right? The velocity of the source. This would be a right angle. This would be the angle coming off the plane. And so if I draw a V shape here, where this is the right angle, and this is the velocity times time of the wave, and this is velocity of source multiplied by time, This then is what we will call the angle here. If I write sine of the angle, what will I get? Yeah, and the p's cancel off. And so this ratio, the velocity of the, the velocity of the wave divided by the velocity of the source then represents that angle. The reciprocal of this, velocity of source to the velocity of the wave, is what we refer to as its Mach number here. And say, how many times faster is the plane going than the speed of sound? But it will make that little wedge. I'll finish by saying, I think most of you are familiar with this wedge when it comes to water waves. It's the same physics. We call this a wake at the end of the boat. Well, water waves travel so slow that seldom do boats go slower than water waves. And so they always seem to be making a wake. But if they do go slower, they don't make a wake. It's when they get faster. And the faster the boat goes, the narrower that wake becomes. And so this is what we would call a shock wave if these were in the air, a bow wave if they were in the water. But the physics is still the same. Make sure you caught this, though. Many people think that a shock wave only occurs when the plane goes from a subsonic to a supersonic. Is that what I'm trying to say here? No, this shock wave always is occurring as long as the plane is going faster than the speed of sound. And I think people perceive that it only happens once because if you were standing down here, you only hear it once. The wave only comes to you one time. A lot like if you were on the beach when a boat goes by, the wave only gets to you once, and then it gets to the other people, and then the other people, and the boat is always making a wake. It didn't make it just one time. And so that's our Mach number and our speed of sound. All right, well, timing worked out good, except no examples for you. So good luck on the homework. You're on your own. You're got to put on your, my wife likes to say, your big boy panties and big girl panties and fight on.
If you have two planes together, like in a line, would the second one, would